Okay, so what happens when we don't know what the population is? So in these examples so far, we've been trying to come up with a confidence interval to estimate the population mean. And that estimate has depended on finding the standard error of a sampling distribution, which meant that we knew what the population standard deviation is. But in most cases, when we don't know actually to find the standard deviation, that depends on knowing what the population mean is. So in most situations, we don't know either of these values. We don't know much about the population. So what was a very natural thing to do is, well, if I don't know what mu is, let me use the plug-in principle and say, I'm going to calculate that statistic from my sample and use that in place of mu. So if we don't know what the population standard deviation is, it makes sense that we calculate the standard deviation for the sample and we use that instead. So what I mean by that instead is now when we calculate, say, the z-score of our sample, I would calculate how far is that from the mean, and then we're going to divide that by the standard and estimate for the standard error. And this estimate we can get by using the standard deviation from the sample and dividing by the square root of n. And so when I do that and I look at the distribution of the z-scores of our samples, the distribution looks like this. So it looks pretty normal. So it looks like by replacing the sigma with an s, we haven't really changed much. But if we compare this plot to the plot of a standard normal distribution, looking at the QQ plot to compare these two, we can see that there is some deviation from the standard normal distribution, that it's symmetric, but looking at this edge over here, we can see that actually we have more stuff on the edges than the sampling distribution should have. So we get a symmetric distribution, which is bell-shaped, but the ends of the bell are a little bit fatter than what we have with normal distribution. So when we don't know what the population standard deviation is, using the standard normal distribution as our model for the sampling distribution of the mean is not going to be a good model. And in fact, we can come up with a better model for that sampling distribution using what's called a t-distribution. Now let's generalize this process for how we would construct a confidence interval for a mean when we don't know what the population standard deviation is. So first thing is we're going to use a different distribution because, as we saw, the normal distribution is not the most accurate model. So we're going to call this a t confidence interval because we're going to use a t distribution as the underlying model for the sampling distribution. So now we have a population x, which we're going to assume is normal and comes from some mean and some standard deviation that we don't know. And we're going to pick a sample of n values, and we want to find the confidence interval for the mean. So two changes that we made from the previous case is, first of all, when we don't know what sigma is, we use s to plug in place of sigma. So that's one change to the formula. And the second change is now, instead of using z alpha over 2, we're going to use what's called t alpha over 2. So basically, instead of using a normal distribution, we've got some other distribution which looks like it, but it's a t distribution. But otherwise, we're going to find this the same way as what we did with normal distribution, which is, plug in the confidence level in the middle and then figure out what t alpha and minus t alpha over 2 are by using what's called the t distribution. So the formula that we're going to need to enter in R is going to be the QT function. Okay, so if you think about this, it's pretty much the equivalent of the Q norm function. But now, since we're using the t distribution, that's not the formula that we want to use. So we want to use the quantile function for the t distribution, and the first thing you enter is the area to the left. So that would be all of this stuff to the left of t alpha over 2 that I'm shading, in yellow. So it would be both the confidence level and alpha over 2. And what goes over here is what's called the degrees of freedom. So the degrees of freedom is your sample size minus 1. So in the case of the Komodo dragon example, if we wanted to find the 95% confidence interval, but we didn't know what the population standard deviation is, I could calculate the standard deviation of my sample and plug that in over here. Then I could calculate the cutoffs for T alpha and minus T alpha over 2 by using the QT function. Okay, and here, this comes from the confidence level. The 7 comes from n minus 1. Less likely to use now, but in case you're curious, there's also a PT function which can calculate areas underneath a T distribution. So that's kind of the inverse of the previous one. So for this function, you would have a certain T distribution, and if you plugged in 2.5, the PT function is going to tell you what's all the area to the left. Whereas the QT function takes as its first input in area, and what comes out of it is the T value that has that area to the left of it. So yes, we use a T distribution as the underlying model for our sampling distribution. And there is also an entire command built into R that can construct this confidence interval for us by using a t-test command in R. So we'll walk through several examples that are going to use these methods. And I should state that you could also use a t-distribution table to find out what these cutoffs are. But I'm just going to stick to using R for the time being. Maybe in a future example, we can walk through how you would use a t-distribution table for these estimates as well. And so before we move on to examples, one last thing I just want to clarify is what exactly is a t-distribution? How does changing the degrees of freedom affect it? How is it related to a normal distribution? So in the plot in the middle, we've got a whole bunch of curves. And so the normal distribution is the dashed one in black up here. And if we compare that to, say, a t-distribution that has 1 degree of freedom, you can see here, similar to what we were looking at with our QQ plot, it almost looks like a normal distribution. It's symmetric and bell-shaped, but the t-distribution has less stuff in the middle and more stuff on the edges over here. So its tails are a little bit fatter. But what's the connection between the degrees of freedom and the shape of this graph? So this graph has one parameter, which is the degrees of freedom that are going to determine what it looks like. And as we increase the degrees of freedom, you can see that the distribution becomes more and more and more normal. And in fact, for the limit as the degrees of freedom goes to infinity, we actually approach the normal distribution exactly. So once you hit about 30 degrees of freedom, once your sample is about 31, there's almost no distinction between the normal distribution and a t-distribution. But with smaller sample sizes, we can see that it's important to use the right distribution because we're ultimately concerned with the cutoffs in the tails. And that's the main difference between all of these distributions. So when we don't know what the population standard deviation is, then we use this t-distribution with degrees of freedom equal to our sample size minus 1. And let me just say that the previous slide kind of stated, here's how we can construct a t-estimate if x is from a normal distribution. We don't really need the population to be normal, but if the population is symmetric, that is usually enough to use an underlying t-distribution. So even if our sample sizes are small, even if they're less than 30, as long as we can assume that the population is symmetric, then the t-distribution is going to be a good model for the sampling distribution.